So a little bit about myself. I'm an associate professor of computer science. I have an easy email, rpm@ucf.edu. So I'm the director of the Extended Reality and Training Lab, or we call it the XRT Lab. Here's some information about my citations. I'm a previous recipient of the NSF Career Award. To date, I'm credited with over $1.2 million in external funding from NSF, Northrop Grumman, Intuitive Surgical, Oak Ridge National Laboratory. In terms of teaching, I'm the Associate Program Director for the Mixed Reality Engineering Graduate Certificate, which consists of the Virtual Reality Engineering course, the AR Augmented Reality Engineering course, and the Mixed Reality Project course. Some information about my teaching evaluations, and I was lucky to be the recipient of this year's CECS Excellence in Graduate Teaching Award. And also, not on the slide here, for those that are unaware, I actually was previously at UT Dallas, got my tenure there, and then I came here to UCF in fall of 2019, right before the pandemic hit. So a little bit overview of my research. My research primarily focuses on extended reality and virtual reality technologies to facilitate and enhance training and education, primarily human training and education, though we're also getting into machine training now. Today, I'm primarily going to be talking about the previous robotic operating room application that we developed with Intuitive Surgical and some research that we conducted for that environment. Just to give a quick overview of some of the other active projects we have going on. With Northrop Grumman, we're actually working on creating a guidance system for a UH-60 Black Hawk helicopter. So we've already managed to co-localize a virtual cockpit on top of a physical cockpit, which will allow us to provide certain cues. And then this picture below that you see of the baby, this is a mixed reality system that we've developed. We're using the MetaQuest Pro. Basically, we co-localize a virtual baby in the same location as a physical baby mannequin, such that when the user goes to touch the virtual baby, their finger will actually come into contact with the physical mannequin, while simultaneously appearing to touch the virtual baby. This basically elevates their senses while also allowing us to do things like having the baby's hand respond to the user's touch, which the mannequin cannot do. And then also I'm leading a CCRI project called iSpies, where essentially what we did in the lower right here, you'll see a real world photo of Greek Park. We essentially laser scan Greek Park using a terrestrial laser scanner. We then took the point cloud that was generated from that, we cleaned it up, we stuck it into 3ds Max, and using ray tracing, we've been able to create fairly photorealistic synthesized images. The nice approach here is we can actually put our virtual camera anywhere within the point cloud and take a picture, even though we didn't necessarily take a real world picture or scan from that location. The idea being that we can now provide data sets that could be of rich use to the computer vision and machine learning communities. But again, as I mentioned, primarily the focus of today's talk is machine learning VR tracking data. I'm focused primarily on the fact that VR applications afford rich tracking data from the head, the hands, sometimes the eyes if you have the correct headset.
Use this fresh release kit from the Vision Cart.
And our goal here was to use VR tracking data to predict educational VR training outcomes. So here you see our robotic operating room training application, which was developed in collaboration with Intuitive Surgical. The goal of the application was basically to teach the trainee how to troubleshoot the DaVinci Xi system when it faults. And it walks them through all of the psychomotor skills required to do so.
The patient side assistant is holding the instrument carriage.
And as you see the user moving here,
okay, the patient side assistant has put the long end of the wrench into the grip release socket.
There's a lot of rich information.
They've turned the wrench a quarter turn counterclockwise to open the grips.
So we have
the patient side assistant has visually verified that the grips are no longer grasping tissue.
So we have the positions and orientations of the two handheld controllers, in addition to the position orientation of the user's headset. So this provides very rich information, and this is the information that we were basically looking to leverage. So basically, we conducted a two-session user study with 60 participants. We had 49 males and 11 females. So essentially what would happen is they would come in for session one. Simple informed consent, we give them a quick Steam VR tutorial to eliminate the wow factor of VR. We then introduced them to our VR training application. We gave them a series of UX questionnaires, and then and that stands for user experience questionnaires, and then we gave them a knowledge test. So just want to point out here, one of the things we want to predict was knowledge acquisition. So basically this knowledge test that occurs right after the training application was our metric for knowledge acquisition. Then 1 week later, they would come back for session 2. We would administer the same knowledge test again. So this was our metric for knowledge retention. They would then go into a practice version of our VR training application where, which is actually what you saw, the video I showed was from the practice application. The training application includes a whole bunch of interaction cues and guidance and directions for the user. But this VR practice application is our metric for performance retention. And then we had a simple exit survey. So in terms of machine learning, we wanted to investigate how various input features could be used to predict our VR training outcomes. So we were interested in both the positional aspects and the velocity-based aspects of the tracking data. And keep in mind, we have the head-mounted display and the 2 controllers. And we also, for each one of those devices, we have linear values. So for example, the linear position of the headset, in addition to the angular values of the headset, so like the quaternion representation of the orientation of the headset. And then same thing for the controllers, we also had linear and angular representations. And we were looking at these different combinations. So for example, looking at linear and angular for both the headset and the controllers, looking at linear and angular for the headset, but linear only for the controllers, and then looking at just linear for both the HMD and the controllers. We use basically principal component analysis to essentially determine which features should be fed into our machine learning models. We then use simple support vector machines for binary decision making. So what we were doing here is we wanted to classify users whether they were a high learning gain individual or a low learning gain individual. And I can use this table above to kind of briefly explain. So essentially for each one of these metrics, we had a mean score and a standard deviation. And if a participant scored 2 standard deviations above the mean, we considered them a high learning gain individual. Otherwise, we classified them as a low learning gain individual. And essentially, we were trying to predict for all 3 of these what the outcomes would be. And this is our user level classification. Here's a very dense overview of our results. With regard to knowledge acquisition, not only did we consider overall accuracy, but due to the unbalanced distribution of high learning gain individuals to low learning gain individuals, we also looked at the MCC score, the correlation coefficient, which is basically a better indication of how well overall our models performed. And as you can kind of see here, the 2 best performers overall, when you account for accuracy, overall MCC, but also testing accuracy, right? It's one thing to score high for training. It's another thing to score well on your testing data set. These were the 2 conditions that overall performed the best. So essentially, position representations, linear and angular for both, or for the headset, and then linear for the controllers. And then velocity base, basically the same combination, linear and angular for the headset and linear for the controllers. When it came to knowledge retention, which is a little trickier, keep in mind this is a week later, so this is really testing people's ability to remember the information. We found that only the velocity-based representations performed well. So this time linear and angular for the headset and the controllers, and also just linear only for both of those. And then with regard to performance retention, which is where the person is basically reperforming the same task in VR, but without any guidance cues, we found one condition that performed particularly well in terms of machine learning, and that was our velocity representation with linear values for both the head-mounted display and the controllers. It performed very well. To understand what was going on under the hood, we did a visual inspection of some of our data. Here in the upper image, you'll see basically one of our low performance users. In the yellow line is basically the HMD representation trajectory. The blue line is the left controller, red is the right controller. And anytime one of these devices peaked over 1 meters per second, so the velocity went over 1 meters per second, we essentially drew a little green arrow or caret between all three of the lines to indicate that there was a peak. So if you take a look at the low, there's a lot of squiggly lines. So there's a lot of variability in their motion. It's not very smooth. And there's also not a lot of arrows. So there's not a lot of velocity peaks. On the other hand, though, if you take one of our high performance or high learning gain individuals, you'll see that their data has a lot fewer squigglies. It's much smoother. You also see that we have a lot more of these carets. So essentially, when they moved purposely. So they would move with velocities that were greater than 1 meter per second. And essentially what we think that this data is indicating is basically cognition capabilities, right? So if someone is a high cognitive performer, they basically are kind of very still when they don't need to move. And then when they need to act, they act very rapidly and very confidently. Where if you take someone from the low performance condition, they're kind of waverly, they're not quite for sure what they should be doing. And then when they do need to reach out or interact with something, they're more slow about it. So they have fewer peaks. Then what we decided to do was, well, this data is interesting and we're able to predict how well people learn from our VR training application, but can we identify people? And this was actually inspired by a 2020 paper that was in Scientific Reports, came out of Jeremy Bailenson lab at Stanford. They had this study with like 511 people indicating that they could identify people with 95% confidence. So we were interested in applying what they had done to our data sets. The first thing that we did was something very similar to what they did. We essentially took the learning session, we broke it up into, I think it was 10 components or subsessions. And then we basically did 20 Monte Carlo pulls where essentially we would train on the bulk of the data and then test on one of the sessions. This is the same methodology that they used. And you'll see that we got very similar results for both pulling from just the learning session. Our optimal results were somewhere around 90%. And then if you look at the retention session, the gradient boosting machine actually got up to 95%, just like in their study. So did Random Forest. But then what we did, which was very different from their study, was we said, well, can we do it across sessions, right? Because that's more relevant. Because realistically, if you're trying to identify a participant by their tracking data, you probably have some previous example, and now you have some new data, and you want to see if you can identify them. And if you take a look at that, basically it drops significantly. So no longer are we around the 90% accuracy range for identifying these participants. We're dropping much lower down to about the 30 to 40% range, depending on if we're going from learning to retention or retention to learning. And obviously there's a few differences between the various machine learning algorithms themselves. And then what we were curious about was, well, we found velocity to be very useful for predicting these virtual reality training outcomes. Can we also use it for an obfuscation method? So that's what we did. We decided to see if we took the velocity-based representation of all of our tracking data instead of the position-based, and if it would help to basically hide the identity of these participants. And if you see here in the learning to learning, so this is basically here in the lower right on the left-hand side, these values are basically equivalent to the values that you see directly above them, except for instead of using position, we're now using velocity. And you can see that basically, instead of having about 90% accuracy, we're now dropping down from, like between 25 and 35% accuracy, which is pretty large drop. And then even more impressively, if we go across sessions, which, we already showed that going across sessions, you have significant drops in accuracy. But if we use velocity for the encoding, we're getting down to 11 and 13% basically. So essentially we can use velocity encodings to help protect the identity of our participants as opposed to releasing the position, but still those velocity encodings would be quite useful for things like predicting learning outcomes from a VR training application. In terms of future work, I have several new and recommended grants coming down the pipeline. We were just awarded an NSF's, my second NSF CCRI planning proposal. This particular one, instead of laser scanning and creating photorealistic images, we're actually, we've developed a pipeline for basically pulling data from closed source Steam VR applications. So the idea being now other researchers will be able to take any Steam VR application and collect data from it, which could be very useful for the VR and HCI communities. We also have an NSF REDL proposal that's been recommended for funding. This is in collaboration with UT Dallas and Vanderbilt University. Previously using the senior design program here, we developed an application called Qubit VR for basically teaching people about quantum computing and virtual reality. And now we've been awarded this grant to basically expand upon that application and also add some intelligent tutoring to it by using machine learning on the tracking data that we have obtained through the study. And then we also have a DEFCON proposal that's been recommended for funding for a little over $1 million with 1 year base and 2 years option. For that one, we're going to be developing a multiplayer battle drill simulation. And we're going to be collecting information from basically groups of participants going through this and using their tracking data to essentially machine learn and come up with ways to provide intelligent tutoring from a team perspective. And then finally, I would just like to acknowledge that the majority of the research that I've presented here today is actually from Alec Moore's dissertation. He just successfully defended his PhD this past fall. And that work, the underlying operating room application was funded by Intuitive Surgical, and the research itself was funded through my NSF Career Award.